Hey friends, welcome to the YouTube channel All About Electronics. So in this video, we will learn about the large signal model of the BJT. Now in the earlier videos of the BJT, we have discussed the basics of the BJT and we have also seen the different configurations in which the BJT can be used. Now one of the most common application of the BJT is to use it as an amplifier. Now when we say the term amplifier, then it could be either a voltage, current or the power amplifier. But here I am referring to the voltage amplifier. That means whenever we apply a small voltage signal at the input of this BJT, then using the BJT it is possible to amplify that signal. And the common emitter is the most preferred BJT configuration for the voltage amplification. So to use this BJT as an amplifier, we need to apply the DC voltage to the BJT. And it is called the biasing of the BJT. So without the biasing, the BJT won't be able to amplify the input signal. That means if we just connect the output of the microphone between this base and the emitter terminal, then it won't be able to amplify that signal. So when we want to use the BJT as an amplifier, then we need to do the two types of analysis. One is the DC analysis and the second is AC analysis. So using the DC analysis, we can identify the operating point of the circuit and we can identify in which region it is operating. So as we have discussed in the earlier videos, to use the BJT as an amplifier, it should be operated in the active region. Now using the AC analysis, we can know the gain of the amplifier and we can find the input as well as the output impedance of the amplifier, because these are the some of the important specifications of the voltage amplifier. And to do all this analysis, we need to model the BJT. So this transistor model is the equivalent representation of the BJT, which closely represents the transistor characteristics. And this transistor model consists of the familiar circuit elements, so that the analysis of the circuit becomes easier. So based on the magnitude of the input signal, there are two transistor models. One is the large signal model and the second is small signal model. Now when the transistor is used as an amplifier, then it consists of the two components. One is the DC component, which is used for the biasing the transistor, and second is the time varying signal which we want to amplify. So this DC signal is often referred as the large signal, while this time varying signal is referred as the small signal. So to understand the behavior of the device for this large signal model can be used. Now we know that the BJT is nonlinear device. So for such device, when the input signal is large, then the behavior of the device is also nonlinear. So for the analysis, we need the model which also accounts all these nonlinearities. Now the large signal model which we are going to discuss over here is valid only when the BJT is operating in the forward active region. That means whenever the base emitter junction is forward biased and the collector base junction is reverse biased. So now let us draw this large signal model. Now as you are aware, the BJT has the two PN junctions and it can be visualized as if the two diodes are connected back to back. Now in this common emitter configuration, let's say the voltage VCE is constant and we are varying the voltage between this base and the emitter terminal. Now by varying this voltage, if we measure the collector current and if we draw the VI characteristic, then it will look similar to the diode characteristic. And the relationship between this collector current and the base emitter voltage can be given by this expression, where here IS is the reverse saturation current and the VT is the thermal voltage. And if we see this expression, then it is similar to the Shockley's diode equation. So from this equation as well as from this curve, we can say that the base emitter terminal can be represented by the diode. Now in the earlier videos, we have already seen the IC versus VCE curves for this common emitter configuration. That means for the fixed value of VBE or the fixed value of current IB, if we change the voltage VCE, then in this active region, the collector current almost remains constant. That means the current which is flowing from collector to emitter terminal can be assumed to be a constant for the given value of VBE. Or we can represent it as a voltage controlled current source. So this is the equivalent representation of the BJT. Or in other words, This is the large signal model of the BJT in the forward active region. So here the collector current IC is equal to Is times e to the power voltage VBE divided by VT. And as you are aware, IC is equal to beta times IB. That means base current IB can be given as Is divided by beta times e to the power voltage VBE divided by VT. And the emitter current is the summation of this collector current and the base current. That means emitter current IE is equal to beta plus 1 times IB. That means beta plus 1 times Is divided by beta times e to the power voltage VBE divided by VT. So as you can see over here, the collector current depends on the value of voltage VBE. And here, as the relationship is non-linear, so even if the voltage VBE changes by the small amount, then there will be a significant change in the collector current. So if we do the DC analysis using this large signal model, then we always need to deal with these nonlinear equations. And because of that, the analysis of the circuit would become complicated. Now in the earlier videos of the BJT, we have already talked about the various biasing techniques and we have also discussed about the DC analysis. But in the analysis, we never use the nonlinear equations, right? The reason is that we further use the approximation for the analysis. So if you see this IC versus VBE curve, then the variation in the voltage VBE is very small. That means even if there is a small change in the voltage VBE, then there is a significant change in the collector current. So for the DC analysis of the BJT, we can approximate the value of VBE as 0.7 volt. Now let's say for the given circuit, if we want to do the DC analysis, then by applying the KVL equation on the input side, we can find the value of this base current. And then using the expression IC is equal to beta times IB, we can find the value of the collector current as well as the voltage VCE. So of course, this method gives the approximate values of the operating point. And if we want to find the exact values, then we need to do the iterations. For example, let's say using this approximation, we have already found the value of the collector current. Now if we put the value of this collector current in this expression, then from this we can find the value of the voltage VBE. Let's say this voltage VBE is equal to VBE dash. Now using this new value of the VBE dash, once again we can find the value of the base current as well as the collector current. Let's say the new value of the collector current is equal to IC dash. And once again, if we put this value of IC dash in this expression, then we will get the new value of the voltage VBE. Let's say it is equal to VBE double dash. And in this way, we can repeat this procedure until we get the values which are very close to the previous values. That means we can repeat this procedure until the value of VBE n plus 1 is same as the value of VBE n. So of course, it is very time consuming procedure when we do it with the pen and paper. But if we follow the certain criterias, then many times using this approximation, we can get the operating point which is close to the actual value. For example, in the fixed bias configuration, if the voltage VBB is much greater than voltage VBE and this base resistor RB is very high, then the base current and effectively the collector current is almost insensitive to the value of VBE. So in this way, by following the certain criterias and using the approximation, we can get rid of the nonlinear equations. But as we had seen in the earlier videos, this fixed bias configuration is very sensitive to the value of beta. So for that, we had seen that the voltage divider or the collector feedback bias configuration provides the better stability. So this is all about the large signal model of the BJT, which can be used in the forward active region. So in the upcoming videos, we will see the more general large signal model which can be used in the different regions. So if you have any question or suggestion, do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.